Hi, my name is Erica Carlson. I'm a theoretical physicist here at the Purdue Quantum Science and Engineering Institute, and we're delighted to have visiting with us this week Barry Sanders. Barry is director of the Institute for Quantum Science and Technology in Calgary, and he's Thousand Talents chaired professor at University of Science and Technology in China, as well as being a Vajra professor at the Raman Research Institute in Bangalore, so a very international scientist. He's a fellow of several different scientific societies, and he's known for quantum limits on measurement, quantum cryptography, and I'll let you get a little bit more into your current research right now, but the first thing we'd like to ask you is, why are people so excited about all things quantum right now?
Well, so quantum physics back at the beginning of the 20th century was really about tiny things, the atom, molecules. And somehow we were safe through a process called decoherence from having to deal with quantum mechanics at the big scale. But with the nanotechnology revolution, with material revolutions, the quantum mechanics that was relegated to nuclear, atomic, and molecular physics now manifests at much larger scales. And so we're very excited because it changes our concept of the universe at scales that we can work with, at technology scales.
Yeah, so I think that's one of the very exciting things right now is that we are getting into a realm where we can bring these quantum properties to the forefront and control them and design new technologies with them and things like that. Tell us a little bit about what originally attracted you into science. I mean, you have to work hard to become a scientist, you have to get some degrees in there, and then it's hard to find a position in science because it's highly competitive. So can you tell us a little bit about what inspired you to head into science?
Yeah, I started off at university. I went into economics to begin with, and my plan was to become a lawyer. And then I took physics as the elective subject because I wanted to do something fun. And then gradually I started to understand that doing physics could become a career option. I didn't understand that when I first started. And then eventually I dropped all the economics. I kept doing physics, still planning to go into law. And then I wound up eventually in a PhD program. And eventually it was too late to go into law, and here I am in physics.
Right, and you're still in physics.
Still in physics, waiting, still haven't had to start a real job yet.
Well, I think that's great, right? I mean, I run into a lot of scientists who kind of feel that way. We sort of sit back and wonder, isn't it fantastic that we get paid to do what we do, because it's actually, it's very fascinating work. It's very fulfilling work. It's very hard work. I mean, we have to work hard. There's long hours, okay? The things don't come easy, but yet at the same time, there's something extremely satisfying when you conquer that problem and really understand something. So speaking of conquering problems, can you tell us a little bit about your research program, what you're working on, and what's something in particular that you are particularly excited about right now in your research program?
Yeah, so I do a number of different projects, quite varied, but the one I'm most excited by these days is quantum computing. And the concept of quantum computing is that somehow we're going to build a computer that operates under very different rules, not the same logical basis as computing. And we hope that quantum computing can make hard-to-solve problems easy. But the reason that I'm really fascinated by it is because to me, there's a deep philosophical issue, something that was articulated by Nobel laureate Richard Feynman about 30 years ago. And this is the idea that the question of whether nature is simulatable. Can we describe nature by algorithms on a computer? And Feynman himself was studying quantum computing in the 1980s and wondering whether a quantum computer was necessary to simulate nature. And I feel like in the 21st century, we're having another revolution in our thinking. For example, in the 20th century, the goal was to come up with the equation that described everything, a theory of everything, grand unified theories, and so on. And now I think we're starting to wonder whether nature is described rather than by an equation, but by algorithms. This is what really drives me, is to find the algorithm of the universe.
Okay, that's deep. That's pretty exciting. So as I understand it, you've also been involved in quantum key distribution. Would you like to tell us a little bit about what's exciting there? What's at the forefront right now, and where you think things are heading there?
Yeah, so almost 20 years ago, I got very involved in quantum key distribution. In the 1990s, there were experiments done that were claiming secure quantum communication. But the theory was not very well developed. And so the claims of security were ignoring realities that there were practical ways to hack into the system. So I collaborated with some others, and we developed the first theory that showed how to prove security under practical conditions. And in recent years...
Do practical conditions mean I just have the environment, or I actually have somebody actively trying to listen in?
Yeah,
or I'm going to have a power surge, that
I'll tell you,
the system.
I'll tell you exactly what happened. For example, light in quantum theory comes in photons, single photons. So if you turn on a laser, it's not one single photon at a time. If you turn it down, it's almost one photon at a time, but sometimes you can have a pair of photons or a triple. And so what happens, an adversary could chop up a double or a triple and learn something. So the proof of security ignored the fact that multiple photons can come out at a time. It ignored the way real detectors work that pick up dark counts. And so these things are security compromises that people were ignoring. So that was the kind of stuff that we looked at about 20 years ago. And then in recent times, I'm very excited by the developments that are taking place. We're into a very practical realm now where systems are working and delivering secure messages through optical fiber, ground-based, 1,000-kilometer scale, satellites on a 5,000 to 10,000 kilometer scale. And so we're at a point where quantum cryptography and quantum communication is now working on long scales. It entails more problems, but the field is moving very fast.
Very exciting, very exciting. So I think what you're saying is that in the future, maybe when I have a Skype conversation with someone who's, far away, or I have collaborators all over the world, as you have collaborators all over the world. And so part of the way we get things done is we have, meetings that are in 2 different countries at once, right? So you're saying maybe the next time I have a Skype call with my collaborators in India, maybe not the next time, but, maybe 5 years down the road, 10 years down the road, when will Skype have the quantum encryption option that I can
Yeah, that's
click?
a very good question. So at the moment, the way, so quantum cryptography is available and can be used for secure communication, but it doesn't have the bit rate that we need to build it into the computational infrastructure. So it's set up as a separate unit. I'll tell you what I imagine.
Yeah.
And that's, in the old days, there used to be, you had a computer and there was a turbo button. Do you remember this? So you had your computer, and then you
Yes, I
push
do.
the turbo button. Your computer would overheat, but you'd get a
Yes.
burst of computational power.
Okay.
And so I imagine quantum cryptography. You'd have a Skype
I
message
see,
with me,
okay.
and then you'd say, I'm now going to tell you whether you should or should not do this.
Yeah.
Then you push the turbo button. Then that part is encrypted, and then we keep going.
I see.
So
I see.
that's my imagination of what's going to happen.
Okay, so not just a quantum encryption button, but the return of the turbo button on our computers.
I imagine that because it's too hard right now to deliver the rates that we need for the public key infrastructure.
Yeah. Very interesting. Well, thank you so much for talking with us, and I look forward to more conversations with you this week as you're visiting us at the Purdue Quantum Science and Engineering Institute.
Thank you.